Hey everybody, my name is Chris and I'm a tutor here at Chegg.com. I mostly do math and a little bit of computer science, and in this video we're going to talk about how differentiability implies continuity. So in other words, if a function is differentiable at a point, then the function is necessarily continuous at that point, and we're going to see why that's true. So remember, there are a lot of different ways to explain what continuity is and to say what it actually means, but the way that we're going to use it here in this video is the limit as x approaches c of f of x equals f of c. Okay, so this is the thing that we want to show. So we want to show this. WTS is a common abbreviation in math for want to show. So we want to show this. Okay, and that's a W. Now, this is actually equivalent to what we'd get if we subtract f of c from both sides. So if we subtract f of c from both sides, we're going to get the limit as x approaches c of f of x minus f of c equals 0. And because f of c is just a constant, we can actually toss it inside of the limit like this. Okay, because c is a fixed constant value of x, so f of c is a fixed constant value of f of x. All right, so we can toss f of c inside the limit, which is why it's okay to put the square brackets like this. So what we're actually going to do is show this. So this is what we want to show. Okay, so we want to show that this expression over here equals 0. So we want to show that this equals 0. So let's go ahead and do that. So let's start with the limit as x approaches c of f of x minus f of c. And then what I want to do is on the inside of the square brackets there, I am going to multiply and divide by something. So I want to say f of x minus f of c, and then I'm going to multiply and divide by the same thing. So let's go ahead and multiply and divide by x minus c. Right, now why is it okay to do that? Well, because x minus c divided by x minus c is essentially just 1. Well, it is just 1. So we're just multiplying by 1 in a way that's useful to us. And now we can, let's go ahead and rearrange things just a bit. So we're going to have the limit as x approaches c of f of x minus f of c, that expression divided by x minus c. And then we still have the other factor of x minus c out here. Okay, so we have this going on now. So all we did was we just took this x minus c and put it underneath this here. Okay, so now what we're going to do is split up the limits of the product as the product of the limits. So let's go ahead and go to the next page. So this is equal to the limit as x approaches c. So let me actually rewrite the last thing we had, because we still want to talk about that a little bit. Over x minus c times x minus c. Now we're going to split this up as the product of two limits. F of x minus f of c divided by x minus c times the limit as x approaches c of x minus c. Okay, now we have to be very careful because it's only okay to do this if both of these limits exist. Okay, so if you have the limits of some product a, b, then we can only split it up as the limit of a times the limit of b if this limit and this limit both exist. All right, so we have to be very, very careful about that. Well, we're going to go ahead and show that both those limits exist. And actually what's nice is, first of all, this one's much easier to look at, so let's just look at that. So this equals, we can just do this by direct substitution. So if we take the limit of this as x goes to c, then what we get is c minus c, which is just 0. Okay, so this limit right here is just 0. That's good. Now, what about this limit here? So notice, actually, this is the alternate definition of the derivative. So let's go ahead and go to page 3. So if we want to say f primed of c, then the standard, so to speak, definition of the derivative is the limit as h goes to 0 of f of c plus h minus f of c, all divided by h. Okay, but an alternate definition is actually the limit as h goes to the limit as x goes to c of f of c minus f of x divided by, sorry, I got that backwards, f of x minus f of c. It's actually not going to matter, but just to keep things the same as how we have them. F of x minus f of c divided by x minus c. Okay, so this is the alternate definition of the derivative. And you can see if we make a substitution with the h's and the x's, so we don't want to get too much into the details with that, but this is the alternate definition of the derivative. and it's typically covered in standard Calculus 1 courses shortly after this definition is introduced. So as it turns out, this whole thing is equal to, well, let's write this. This is just f primed of c. So the entire thing then is equal to f primed of c times 0, which is just 0. Now, why is it okay to say that this times that equals 0? So you might be thinking, well, yeah, anything times 0 is 0. Well, this is only going to work if this actually exists. So if the derivative doesn't exist, or if it shoots off to infinity or negative infinity, then we can't say this. However, we know that this exists because what we're trying to do is show that differentiability implies continuity. So we're actually working under the assumption that the function is differentiable at c. So we're assuming f primed of c exists and is finite, because we're trying to show that differentiability implies continuity. In other words, we're trying to show that if the function is differentiable, then it's continuous. So we have to be operating under the assumption that that differentiability is there, which means we have to be operating under the assumption that f prime of c actually exists and is finite. And that's why it's okay to have this equality here. Okay? Now, then we're pretty much done, actually. Why are we done? Well, remember back here on page 1, we started with this right here. We said that's equal to this, which is equal to this, and then we rewrote that here, and then it's equal to this, which is equal to this, which is equal to 0. So what we've concluded then is that this expression right here equals 0, which is exactly what we wanted to show. Therefore, by definition, by one of the definitions of continuity, we've established that f of x is continuous at c, because we've just shown this essentially. Okay, so we started with well, this expression here, we started with that. We wanted to show it 0, and we did a small algebraic manipulation to make use of the fact that the function is differentiable at c. So we did some algebraic manipulations, split up the limit as a product of two limits, which is only okay because both of these limits exist, right? And we used the fact that the derivative exists to show that this limit exists, because this limit is the derivative. So if the derivative exists, of course this limit exists. So all these steps are okay. And that verifies then that this limit is 0, which means, by definition, that the function is continuous at x equals c. Okay, so this has been the proof, more or less, of how differentiability implies continuity. I hope you found it helpful, and thank you for watching.